Hey, welcome back to this fluid series series of fluid mechanics. Name is Theodore, and we are gonna continue talking about energy balance. So we've derived from our last videos this general energy equation. Now, if we manipulate it such that the volume equals to mass divided by the density, and we substitute that in. We just substitute this volume here and this volume here. We will get this equation. So I've just substituted the volume in by mass over rho. And if I want to factorize the mass out, I can do so. So I'm factorizing the mass out, and then I'm going to divide throughout by the same mass flow rate. So once I do that, I will get this equation. Okay, I'll get this equation, and this assumes we must have a constant mass flow rate in and out. So if we are talking from a fluid, for example, so take this ball away, just imagine there's a fluid pipe flowing from point A here to point B here. So it's going up and going down. Alright, so this equation will generally hold. And if we cannot assume there's any extra fluid being pumped in along the pipe. Okay, this is a very simple case. So if we ignore the what do you call that? Force, the frictional forces, we will get something like this. And this looks exactly like Bernoulli's equation. Now in the actual derivation of Bernoulli's equation, there will be lots of other things we have to consider. For example, streamlines and how fluid is flowing along the same streamline, blah 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 blah. But in general, as long as our energy equation satisfies, that it's incompressible, or there's the same mass flow rate in and out, and then we have this force by mass. The frictional forces are basically negligible. We can use this equation. So for incompressible flows with negligible force over the frictional forces, this equation definitely applies. So if I have a fluid flowing from point A here, okay, so let me erase, never mind. I have a fluid flowing from point A at the beginning, and then here I will call it point B. I have a fluid going from point A to point B. You see the arrows here. As long as friction here is negligible, and I'm going from point A to point B, I shall use this blue color. I don't care how it flows from point A to point B, as long as there's no the mass coming in here, the mass coming out of here is the same, as there's nothing coming through the walls or anything like that. And we can use the same so-called energy equation that looks like Bernoulli's equation. So this is the very simple way of understanding it. Now, what are the uses of something so simple? Okay, the uses are as follows. Besides it being very easy for us to conceptualize and learn undergraduate fluid mechanics, we can use it to measure flow. For example, in a Venturi flow meter. So what we notice is that, hey, if we have a flat surface, where the elevation is the same, that means that ZA equals to ZB. Okay, we can relate the flow velocity to the pressure drop. So the pressure difference between 2 points is directly correlated to the flow velocity. And since the flow velocity is connected to the the flow velocity is directly connected to mass flow rate or volumetric flow rate, we can use it to measure flow. And that is what we want to discuss in our next video. Okay, so next time you hear Bernoulli's equation, don't be too frightened. It's just the most simplest form of energy balance. I mean, there is a lot more theoretical richness to it. You have to talk about streamlines, but the final mathematical form of the equation applies to more than just a constant streamline, so to speak, that you can trace all these streamlines. As long as the energy equation's like that, you can just use it straight away. That's how I do it. Okay, so thank you very much. We'll continue our next video on Bernoulli flow meters. So see you in the next one. Bye bye.